Hello everyone, this video will cover variability analysis part 2 handout. So I'm going to jump directly to problems that we have in this handout, all right? This handout specifically will cover queuing analysis and the quantitative analysis of lines or queues or wait lines, right? We have two parts in a queuing system. One is the service part. The other part is the line or waiting or buffer part, and together we call it this system. So this system has a waiting part and a service part. In waiting part, customers that come in, if there is no server or clerk or teller or service provider available, they are going to wait in line until a server becomes available. Then they are going to get service, right? We have seen in the past how we can calculate certain metrics for the line, but one of the metrics that was difficult to calculate and we need an additional formula to calculate it is this one, TQ, time in queue, or average amount of time that each customer is going to wait, which is a function of three factors. One of them is variability, the other one is a function of utilization, and the other one is a function of processing time. All right. As I mentioned, there was a typo in this handout, so we are going to add that 1 minus 1 to the power of u equation. All right. Let's see how we can use this formula. This is a problem we have, and there is one clerk. Every 100 seconds, one customer arrives, and the processing time takes, I'm talking about this problem, processing time takes 90 seconds. CV of A and CV of P, they both are equal to 1. The question is that one clerk that we have, what is that clerk's utilization? Well, intuitively, as I mentioned, I don't really like relying too much on formulas. They will work every single time, but there is an intuitive solution for this. Every 100 seconds, one customer arrives, right? On average. And on average, I'm going to spend 90 seconds serving that one customer. So out of 100 seconds, I'm working 90 seconds. So my utilization is going to be equal to 90 over 100, which is at 90%. On average, I'm going to work 90% of the time. Next question, which is the follow-up question, it's this one, example 2. Question is, all right, on average, how long each customer is going to wait in line? Question is asking for TQ. TQ is given by that formula, all right? And CV of A, CV of P, both of them are 1. I'm going to plug in ones here. U is 90% to the power of 2 times C plus 1. C is 1 minus 1 times C times 1 minus U times processing time P or TP. So if you simplify this, that's going to be 810 seconds. On average, every customer is going to wait 810 seconds in line. I went ahead and put together even more examples based on calculated more metrics based on that one example. So let's see what those are. Well, one of them was the most fundamental and challenging one, is calculating TQ, average amount of time in line. Next metric is all right, so we know how long on average each customer waits, but how long on average a customer is going to stay in this process, in this system? Well, every customer is either is in line or that customer is getting service. Total amount of time is going to be equal to time in line plus time in processing, and that is going to bring me to 810 plus average amount of processing is 80 seconds. That's going to be 900 seconds. All right. Now, so far we have calculated server's utilization, we have calculated time in line, we have calculated uh, average processing time. Next, we are going to calculate on average, what is the length of this line? How many people on average are going to stay in this line, right? And that is IQ, inventory of queue, or number of people in line. We are going to calculate that with Little's law. Little's law says IQ equal to R times TQ. R is throughput rate, which is the minimum of rate of arrival and rate of processing. That's going to be 1 over 100. times TQ is 810 seconds. That's going to bring me to 8.1 customers. So on average, 8.1 customers will wait in a line of this, and 8.1 customers will be right here, right there. All right, 8.1 customers. Next question is, on average, how many customers are being processed or are being served at any point in time? Well, there are two ways of calculating that. One is based on formula, the other one is a little bit more intuitive. Let's look at formula first. We are going to use Little's law. IP is equal to R times TP. All right. R is 1 over 100 customers per second times TP is 90 seconds. That's going to bring me to 0.9 customers. So I have IP. Now, next question is, is there a nicer, more intuitive way of solving this problem? The answer is absolutely yes. There's one clerk. Every clerk this clerk works at 90% of the time, which means at that 90% of the time, there's only one customer with that clerk, and 10% of the time, there is no customer with the clerk. Then on average, how many customers are with the clerk? It is going to be equal to 0.9 times 1 plus 0.10 times 0, just average, all right? And that's going to be 0.9 again. Now, how many people are in this system altogether? I'm looking for I, and that is going to be equal to, I is going to be equal to IP plus IQ, which is going to be equal to altogether 9 people. All right. So this is pretty much a typical analysis of a whole system, starting from the setup and ending with calculating pretty much all metrics that we might be interested in. Now let's look at the impact of increasing just tiny bit increase of processing time. In this example, example 3, the question is, what if processing time goes up just by 5 seconds? Instead of 90 seconds, now it is 95 seconds. Well, is the system or this process still stable? Yes, because rate of arrival is less than rate of processing, right? I can process more than what customer asks. And then utilization is going to be equal to 95%. Now my servers are being utilized, or my clerk or server or service provider is being utilized 95% of the time. Let's look at TQ. I'm going to just plug in numbers. There's not much has changed except utilization is 95%, all right? And TP is 95 seconds. Well, if that is the case, that brings TQ or average wait time to 1,805 seconds, all the way from 810 seconds. That is more than double the wait time by only increasing 5% in processing time. Why is that the case? It's simply because we are operating at a very high utilization. Utilization was high to begin with. It was 90%. Now my utilization is 95%. It's a very high utilization. Tiny bit increase in processing time is from 90 to 95% is going to increase my wait time and number of people in line. Remember that relationship that we had. Let me plot it right here. Utilization versus TQ. That was, if this is utilization of 1 or 100%, that relationship was something like this, right? If 90% is right here, increase to 95% is going to increase TQ dramatically. All right, that relationship is not linear, meaning if processing time goes up by 5 seconds, there is no such a thing saying wait time is also going to go up by 5 seconds. That's not the case. You see that here it doubled, more than doubled. It went up from 810 seconds to 1,805 seconds. Let's look at a little bit of a managerial insights here. If your utilization is high, it is very difficult to be responsive to slightest disruption or change. If you really need to be a little bit more responsive, if you long wait times is not an option, there is no other way, then there's no way other than keeping excess capacity or making sure that your utilization is not very high. All right. What is this question comes up in classes all the time. Okay, so what is a good good inside quotations, what is a good number for utilization? Anything 80% or below 80%, its rule of thumb is that is an good utilization. But once you go above 80%, tiniest disruption in process, increase in processing time, is going to have a huge impact on in a mostly negative side, impact on customers. All right, now let's look at one more managerial insight, and that is impact of variability. By increasing variability, you see that by increasing variability right here, again, time in line, amount of time that each customer is going to wait, goes up, right? And again, that relationship is not linear. If you cannot accommodate high wait times, then you need to make extra effort to bring down variability. You can bring down variability in two different ways, because the variability has two sources, at least in the systems that we are discussing. One source of variability is arrival, the other source of variability is processing. If you want to bring down variability in arrival or inter-arrival times, a classic example is use appointments, use scheduling. All right, that is not going to eliminate variability, but definitely that is going to bring down variability. Can we bring down variability in processing time? Absolutely. There is a huge discussion in healthcare that we need to standardize everything. We need to make sure that everyone goes through same, all patients go through, let's say patients that go to emergency department, they go through more or less same procedure, or different group of patients go through the same procedure. Well, that is standardization. One of the main motivations is, besides quality implications, motivation is that standardization brings down variability in processing time. All right. One of the important discussions that we are going to have, and you have read articles about it, is queue pooling, or pulling, or taking advantage of economy of scale. Let's first make sure we define pooling properly. Well, in this system, you see that there are 4 servers, and each server or service provider has its own separate line. If you notice, you can imagine, again, just for the sake of being a little bit clear or dramatic, even. I'm going to assume that there's a wall between each of these 2 servers, meaning customers in one side, one line, they don't see the other server situation. As you can see, there are 3 people or 3 customers waiting in line here, one waiting here, while the other 2 servers, they are not even working. All right, this is a segregated system. This is the one that each server has its own line. What is the alternative to this? Well, alternative to this is something called pooled system. Consider the same system. How many customers, how many servers that we have here? 4. I'm going to have 4 right here. Altogether, how many people are in this system? I have 1, 2, 3, 4, 5, 6. Well, here same thing, 1, 2, 3, 4, 5, 6. But the difference is that in a pooled system, I put all of the customers in just one line. Service providers, clerks, they do not have their own separate line. There is one line that once a server becomes or service provider becomes available, that service provider is going to pull one customer from that line. All right, that's why all 4 servers right here are busy compared to here. All right, here 2 of them are busy and there are people in line, but here all 4 of them are working. As we are going to see in pooled systems, on average, service utilization is the same as a segregated system on average. But because we are avoiding situations where one server is idle while the other server has people waiting for it, because we are avoiding those situations, this pool system is better for customer. It decreases customers' wait time dramatically. Let's quantify that and see if that really is the case. All right, so here's the problem is you have 4 clerks or tellers. Everything is exponential, inter-arrival time, exponential processing time. Inter-arrival time on average is 25 seconds. Processing time is 90 seconds. Question is, uh, how much of a difference between pulled system and segregated system are we talking about? Well, if I write down everything that I have, first let's see if this is a stable process. In a stable process, rate of arrival is less than rate of processing, and that is exactly the case. Here, rate of arrival is 1 over 25, all right? And that 25 is right here. And rate of processing is I have 4 of them, and each of them can process at the rate of 1 over 90 customers per second, all right? That's 1 over this 90 right here. So this is number of servers or clerks or tellers, and this is a processing rate of each one of them. Altogether, I'm gonna have a rate of processing that is more than rate of arrival. As a result, this is a stable process. Now let's investigate the difference between these two systems. Let's quantify that. Let's just quantify it, all right? All the quantification that happens here, I'm gonna explain them one by one. What do we have here? Well, first we are going to assume that this is everything is pulled. There is no separate lines. Everything is pulled. There are 4 servers right here, and there's a long line here. People come and wait here, and whenever one of these clerks is available, is going to pull from this line. You see this kind of systems in, especially in DMV. All right. Now, utilization is going to be rate of arrival or over rate of processing. That's going to be 90%. TQ is going to be given by this formula, but in this TQ, I'm going to have utilization 90%. C is 4 because I have 4 clerks, and again 4 here times 1 minus 90%, and right there is 90 seconds for processing time. All right, so TQ becomes all together, if you plug in numbers, do the math, everything, it's going to come down to roughly about 180 seconds. 180 seconds. Let's look at that same system, same setup, but segregated lines, meaning every clerk has its own separate line. If that is the case, this is an assumption I'm going to make. I'm going to assume that each of these clerks receives 1 quarter of those customers. Let's think about it. 1 quarter of those customers, which means rate of arrival is going to go down by 1 quarter, and that's exactly what I have here. Because I'm assuming that each of them are going to receive 1 quarter of arrivals, I don't have to analyze 4 of them separate from each other. I can analyze just one of them, and then the other ones are identical to this one. All right, but in analyzing that one, I want to make sure that rate of arrival and processing, everything is determined correctly. So let's walk through that. I have 1 server, coefficient of variation for arrival, CV of A and CV of P the same, 1, processing time 90 seconds, rate of arrival is 1 quarter of, let me go up a little bit. Rate of arrival is 1 quarter of 1 over 25, which was rate of arrival of total. All right, that's going to be 1 over 100. Utilization still is going to be 90%. Look, utilization is 90% here, 90% up here, right? Utilization did not change. On average, my servers are working 90% of the time. Now, TQ, time in line, is going to be given by this formula, but this U is 90%, C is 1, and this C is 1 as well, all right? Nothing else has changed. That is going to bring my average customer's wait time to 810 seconds compared to 180 seconds. Up here, 179 seconds. You see that right here? It's 810 seconds. That's a dramatic increase in wait time, and that is the power of economy of scale, or power of pulling customers together. All right, with that, I hope that is clear, the power of pooling and why pooling is such a big deal. Well, what are the benefits of pooling? Pooling creates a little bit of sense of fairness among customers. It creates also a sense of fairness among service providers, and also customers, of course, wait way less. What are the limitations of pooling? Well, pooling usually, and at least at times, may lead to a very long line, even though that line moves faster, but because it's a long line, that might interrupt with your process regular operations. For example, a while ago, I was at Costco and I realized they are pulling their lines, but that line goes all the way to the end of the store, and it was very difficult for other customers to go around that line and go from one aisle to another aisle. So pulling, that's one of the biggest problems that pooling has. Another problem that might arise from pooling is that because servers pull from the line, um, in situations where one customer has a specific relationship, specific relation with one specific server, knows that server and wants to get service from that specific server, you might interrupt that kind of relationship that a customer has with the service provider. Another problem that we need to be careful about is that pooling might actually hurt some customers at the benefit of benefiting other customers. For imagine situation where um, in a grocery store you are pulling all customers in one line, meaning even that customer that who has purchased just one, um, let's say one bag of bread, all right, or just one pack of chewing gum, that customer is going to stay in line, possibly behind someone who has a full cart of items, all right. In this case, yes, on average you are bringing down average customers average wait time, but that one customer is going to feel, okay, you know what, I'm just buying a pack of gums, why do I have to wait behind this customer? That's why behind this customer with full cart of items. So that's why usually rule of thumb is that if you want to really rule of thumb is if customers processing times are homogeneous, they are close to each other, it makes perfect sense to pool. If physically your store allows that, if there's a space for longer lines. But if there is a huge variability among customers' processing time, then it makes perfect sense to segregate customers based on their processing time, and then in each group pull them. For example, in grocery store, usually there's one line for 15 or less items and one line for people with full cart or full basket. And that's a logic behind it. That full basket customers, they have longer processing time, they stay in one line, and the other customers that don't have that have lower processing time, they stay in a separate line. All right. Now that brings us to some of the more psychological, that is the right word to use, psychological aspects of waiting line. And this is a perfect time to talk about it because of the COVID vaccine. And this is always a question. If there's a line, how should we prioritize people in line in case of vaccine? Should we give priority to older people? Should we give priority to younger people because they have um, higher life expectancy? It's one of those questions that it can discussion about it can get very heated. It can be very heated, but here's the thing: any service provider knows that the waiting is part of their service. Waiting is part of their service. How can we make sure that customers' wait is less painful? Well, provide comfort. Make sure that they are waiting in a pleasant environment. Provide distraction. Make sure that you put these magazines that we all know they are these titles are not so realistic. Put them in front of a customer, and they are going to distract themselves. You don't have to work too hard. All right. If you see anyone, if you see something like, I don't know, Trump and Obama dance off to Despacito, well, you're gonna grab that magazine and just for laughs, you're gonna open it and have a look at it. All right, that is the whole idea, just to distract you from waiting or provide information. If you look closely at this image that we have here, it says this is from, by the way, from year 2013, almost 10 years ago, from Shanghai airport. Queuing and processing time less than 10 minutes for 95% of passengers in Terminal 1 and 2. This is a perfect information provided to customer that, listen, if you are going to Terminal 1 and 2, there's a 95% chance that you are going to wait, you are going to go through possibly 10 minutes or less of wait time, right? Wait time altogether. So your whole processing is going to be roughly about 10 minutes or less. When you provide information to customer regarding wait time, customers usually they find a way to entertain themselves, right? But blind waits are they feel a lot longer. Provide explanation, right? This happens a lot in among airliners. If because of weather customers are waiting, if because of because they don't have staff or pilots, or because of I don't know, traffic, pilot is stuck in traffic, heavy traffic, explain it to customer. Provide explanation and, listen, this is what's happening, this is why you are waiting. If you provide a explanation and provide information that your flight has been delayed for 2 hours, customers usually find a way to entertain themselves, right? Manage expectations. Airliners used to do this a lot, and still they find a way to do it in a legal way, and that is providing a little bit pessimistic estimates of flight time. If flight from Los Angeles to JFK is going to take 5 hours, they find a way to provide a little bit pessimistic estimates. Let's say 5 hours and 15 minutes. If flight arrives in 5 hours and 5 minutes, everyone is happy that, yay, we arrived 10 minutes early. But as a matter of fact, you have arrived with 5 minutes delay. But because they have managed your expectations, you are happy. All right. Again, federal government was a little bit strict on this, but still there are ways of measuring what is exactly flight time, when does that start. They always dance around those measurements to make sure that they can provide, when necessary for certain flights, provide a little bit of a pessimistic estimates. Ensure fairness. When you feel everyone is, you are waiting in line, but you are not the only one. Everyone is waiting at the same time, not at the same line. Usually, it's easier to wait. But when someone cuts the line, then that becomes a little bit frustrating. Create a sense of being in a group among customers. This is I have a personal experience with this. When I was buying my very first iPhone long time ago, I waited in line overnight in front of AT&T store. And what happened was that roughly around 4 a.m., this AT&T, one of the managers or staff showed up. They opened the store. They served everyone coffee. Up to that point, no one was talking to someone else. But once they served coffee, started forming groups. We found ourselves, in groups of 2, 3 that we were talking to each other, and that was a lot more pleasant experience compared to waiting until 4 a.m. Because again, until 4 a.m., no one was talking to each other. It was but after 4 a.m., there was a sense of, okay, I'm in a group of 2, 3, 4, 5 people waiting, and I'm not the only one waiting. We all are waiting in the same line. All right. So being in a group makes waiting a little bit less painful. With that, I'm going to stop. These are things that sort of takeaways from this handout. I hope you find this useful. Let me know if you have any questions.